Unconventional oil is petroleum produced or extracted using techniques other than the conventional method. Oil industries and governments across the globe are investing in unconventional oil sources due to the increasing scarcity of conventional oil reserves. Sources of unconventional oil. According to the International Energy Agency's World Energy Outlook 2001, unconventional oil included oil shales, oil sands-based synthetic crudes and derivative products, coal-based liquid supplies, biomass-based liquid supplies, gas to liquid, liquids arising from chemical processing of gas. In the IEA's World Energy Outlook 2011 report, unconventional oil include d. extra heavy oil, natural bitumen, kerogen oil, liquids and gases arising from chemical processing of natural gas, coal to liquids and additives. Defining unconventional oil. In their 2013 webpage jointly published with the Organization for Economic Cooperation and Development, the EIA observed that as technologies and economies change, definitions for unconventional and conventional oils also change. Conventional oil is a category that includes crude oil, and natural gas and its condensates. Crude oil production in 2011 stood at approximately 70 million barrels per day. Unconventional oil consists of a wider variety of liquid sources including oil sands, extra heavy oil, gas to liquids and other liquids. In general, conventional oil is easier and cheaper to produce than unconventional oil. However, the categories a conventional and unconventional do not remain fixed, and over time, as economic and technological conditions evolve, resources hitherto considered unconventional can migrate into the conventional category. According to the U.S. Department of Energy, unconventional oils have yet to be strictly defined. In a communication to the UK entitled Oil Sands Crude in the series The Global Range of Crude Oils, it was argued that commonly used definitions of unconventional oil based on production techniques are imprecise and time-dependent. They noted that the International Energy Agency does not recognize any universally accepted definition for conventional, or unconventional oil. Extraction techniques that are categorized as conventional use unconventional means such as gas reinjection or the use of heat, not traditional oil extraction methods. As the use of newer technologies increase, unconventional oil recovery has become the norm, not the exception. They noted that the Canadian oil sands production predates oil production from areas such as the North Sea. Under revised definitions, petroleum products, such as Western Canadian Select, a heavy crude benchmark blend produced in Hardisty, Alberta, may migrate from its categorization as unconventional oil to conventional oil because of its density, even though the oil sands are an unconventional resource. Oil sands equals. Oil sands generally consist of extra heavy crude oil or crude bitumen trapped in unconsolidated sandstone. These hydrocarbons are forms of crude oil that are extremely dense and viscous, with a consistency ranging from that of molasses for some extra heavy oil to as solid as peanut butter for some bitumen at room temperature, making extraction difficult. These heavy crude oils have a density approaching or even exceeding that of water. As a result of their high viscosity, they cannot be produced by conventional methods, transported without heating or dilution with lighter hydrocarbons, or refined by older oil refineries without major modifications. Such heavy crude oils often contain high concentrations of sulfur and heavy metals, particularly nickel and vanadium, which interfere with refining processes, although lighter crude oils can also suffer from sulfur and heavy metal contamination too. These properties present significant environmental challenges to the growth of heavy oil production and use. Canada's Athabasca oil sands and Venezuela's Orinoco heavy oil belt are the best-known example of this kind of unconventional reserve. In 2003, the estimated reserves were 1.2 trillion barrels. Heavy oil sands and bituminous sands occur worldwide. The two most important deposits are the Athabasca oil sands in Alberta, Canada, and the Orinoco heavy oil belt in Venezuela. The hydrocarbon content of these deposits is either crude bitumen or extra heavy crude oil, the former of which is often upgraded to synthetic crude and the latter of which the Venezuelan fuel or emulsion is based. The Venezuelan extra-heavy oil deposits differ from the Canadian bituminous sands in that they flow more readily at Venezuela's higher reservoir temperatures and could be produced by conventional techniques, but the recovery rates would be less than the unconventional Canadian techniques. In 2011, Alberta's total proven oil reserves were 170.2 billion barrels, representing 11% of the total global oil reserves and 99% of Canada's oil reserves. By 2011, Alberta was supplying 15% of the United States crude oil imports, exporting about 1.3 million barrels per day of crude oil. The 2006 projections for 2015 were about 3 million barrels per day. At that rate, the Athabasca oil sands reserves would last less than 160 years. About 80% of Alberta's bituminous deposits can be extracted using in situ methods such as steam-assisted gravity drainage and 20% by surface mining methods. The northern Alberta oil sands in Athabasca, Cold Lake and Peace River areas contain an estimated 2 trillion barrels of crude bitumen and extra-heavy oil, of which 9% was considered recoverable using technology available in 2013. It is estimated by oil companies that the Athabasca and Orinoco sites have as much as 2/3 of total global oil deposits. They have only recently been considered proven reserves of oil. This is because oil prices have risen since 2003 and costs to extract oil from these mines have fallen. Between 2003 and 2008, world oil prices rose to over $140. And costs to extract the oil fell to less than $15 per barrel at the Suncor and Syncrude mines. In 2013, crude oil from the Canadian oil sands was expensive oil to produce, although new U.S. tight oil production was similarly expensive. Supply costs for Athabasca oil sands projects were approximately $50 to $90 per barrel. However, costs for Bakken, Eagle Ford and Niobrara were higher at approximately $70 to $90 according to 135 global oil and gas companies surveyed, reported by the Financial Post. Extracting a significant percentage of world oil production from these deposits will be difficult since the extraction process takes a great deal of capital, manpower and land. Another constraint is energy for project heat and electricity generation, currently coming from natural gas, which in recent years has seen a surge in production and a corresponding drop in price in North America. With the new supply of shale gas in North America, the need for alternatives to natural gas has been greatly diminished. A 2009 study by CERA estimated that production from Canada's oil sands emits about 15% more carbon dioxide, over the well-to-wheels lifetime analysis of the fuel, than average crude oil. Author and investigative journalist David Strahan that same year stated that IEA figures show that carbon dioxide emissions from the tar sands are 20% higher than average emissions from oil. Tight oil Tight oil, including light tight oil, is crude oil contained in petroleum-bearing formations of low permeability, often shale or tight sandstone. Economic production from tight oil formations requires the same hydraulic fracturing and often uses the same horizontal well technology used in the production of shale gas. It should not be confused with oil shale, which is shale rich in kerogen, or shale oil, which is synthetic oil produced from oil shales. Therefore, the International Energy Agency recommends to use the term light tight oil for oil produced from shales or other very low permeability formations, while World Energy Resources 2013 report by the World Energy Council uses the term tight oil. Oil shale Oil shale is an organic rich fine-grained sedimentary rock containing significant amounts of kerogen from which technology can extract liquid hydrocarbons and combustible oil shale gas. The kerogen in oil shale can be converted to shale oil through the chemical processes of pyrolysis, hydrogenation, or thermal dissolution. The temperature when perceptible decomposition of oil shale occurs depends on the time scale of the pyrolysis. In the above-ground retorting process, the perceptible decomposition occurs at 300 degrees Celsius, but proceeds more rapidly and completely at higher temperatures. The rate of decomposition is the highest at a temperature of 480 degrees Celsius to 520 degrees Celsius. The ratio of shale gas to shale oil depends on the retorting temperature and as a rule increases with the rise of temperature. For the modern in situ process, which might take several months of heating, decomposition may be conducted as low as 250 degrees Celsius. Depending on the exact properties of oil shale and the exact processing technology, the retorting process may be water and energy extensive. Oil shale has also been burned directly as a low-grade fuel. Estimates of global deposits range from 2.8 to 3.3 trillion barrels of recoverable oil. There are around 600 known oil shale deposits around the world, including major deposits in the United States of America. Although oil shale deposits occur in many countries, only 33 countries possess known deposits of possible economic value. The largest deposits in the world occur in the United States in the Green River Formation, which covers portions of Colorado, Utah, and Wyoming. About 70% of this resource lies on land owned or managed by the United States federal government. Deposits in the United States constitute 62% of world resources. Together, the United States, Russia and Brazil account for 86% of the world's resources in terms of shale oil content. These figures remain tentative, with exploration or analysis of several deposits still outstanding. Well-explored deposits, potentially possessing economic value, include the Green River deposits in the western United States, the tertiary deposits in Queensland, Australia, deposits in Sweden and Estonia, the El Lajun deposit in Jordan, and deposits in France, Germany, Brazil, Morocco, China, southern Mongolia and Russia. These deposits have given rise to expectations of yielding at least 40 liters of shale oil per ton of shale, using the Fisher assay method. According to a survey conducted by the RAND Corporation, the cost of producing a barrel of oil at a surface retorting complex in the United States would range between $70 a euro 95. As of 2008, industry uses oil shale for shale oil production in Brazil, China and Estonia. Several additional countries started assessing their reserves or had built experimental production plants. In the USA, if oil shale could be used to meet a quarter of the current 20 million barrels per day demand, 800 billion barrels of recoverable resources would last for more than 400 years. Thermal depolymerization Thermal depolymerization has the potential to recover energy from existing sources of waste such as petroleum coke as well as pre-existing waste deposits. This process, which imitates those that occur in nature, uses heat and pressure to break down organic and inorganic compounds through a method known as hydrous pyrolysis. Because energy output varies greatly based on feedstock, it is difficult to estimate potential energy production. According to Changing World Technologies, Incorporated, this process even has the ability to break down several types of materials, many of which are poisonous to both humans and the environment. Coal and gas conversion Using synthetic fuel processes, the conversion of coal and natural gas has the potential to yield great quantities of unconventional oil and/or refined products, albeit at much lower net energy output than the historic average for conventional oil extraction. In its day, prior to the drilling of oil wells to tap reservoirs of crude oil, the pyrolysis of mined solid organic rich deposits was the conventional method of producing mineral oils. Historically, petroleum was already being produced on an industrial scale in the United Kingdom and the United States by dry distillation of cannel coal or oil shale in the first half of the 19th century. Yields of oil from simple pyrolysis, however, are limited by the composition of the material being pyrolyzed, and modern oil from coal processes aim for a much higher yield of organic liquids, brought about by chemical reaction with the solid feedstuff. The four primary conversion technologies used for the production of unconventional oil and refined products from coal and gas are the indirect conversion processes of the Fischer-Tropsch process and the Mobil process, and the direct conversion processes of the Burgess process and the Carrick process. Sasol has run a 150,000 barrels per day coal-to-liquids plant based on Fischer-Tropsch conversion in South Africa since the 1970s. Because of the high cost of transporting natural gas, many known but remote fields were not being developed. On-site conversion to liquid fuels are making this energy available under present market conditions. Fischer-Tropsch fuels plants converting natural gas to fuel, a process broadly known as gas to liquids, are operating in Malaysia, South Africa, and Qatar. Large direct conversion coal to liquids plants are currently under construction, or undergoing startup in China. Total global synthetic fuel production capacity exceeds 240,000 barrels per day, and is expected to grow rapidly in coming years, with multiple new plants currently under construction. Environmental concerns. As with all forms of mining, there are hazardous tailings and waste generated from the varied processes of oil extraction and production. Environmental concerns with heavy oils are similar to those with lighter oils. However, they provide additional concerns, such as the need to heat heavy oils to pump them out of the ground. Extraction also requires large volumes of water. The environmental impacts of oil shale differ depending on the type of extraction. However, there are some common trends. The mining process releases carbon dioxide, in addition to other oxides and pollutants, as the shale is heated. Furthermore, there is some concern about some of the chemicals mixing with groundwater. There are processes either in use or under development to help mitigate some of these environmental concerns. The conversion of coal or natural gas into oil generates large amounts of carbon dioxide in addition to all the impacts of gaining these resources to begin with. However, placing plants in key areas can reduce the effective emissions due to pumping the carbon dioxide into oil beds or coal beds to enhance the recovery of oil and methane. Carbon dioxide is a greenhouse gas, so the increased carbon dioxide produced from both the more involved extraction process with unconventional oil, as well as burning the oil itself, of course, has led to deep concerns about unconventional oil worsening the impacts of climate change. Economics. Sources of unconventional oil will be increasingly relied upon when conventional oil becomes more expensive due to depletion. Conventional oil sources are currently preferred because they are less expensive than unconventional sources. New technologies, such as steam injection for oil sands deposits, are being developed to reduce unconventional oil production costs. In May 2013, the IEA in its medium-term oil market report said that the North American oil production surge led by unconventional oils, U.S. light, tight oil and Canadian oil sands, had produced a global supply shock that would reshape the way oil is transported, stored, refined and marketed. See also: extreme energy, renewable energy, future energy development, Hubbert peak, energy development, alternative fuels, Fischer-Tropsch process, synthetic liquid fuels program, world energy resources and consumption, oil megaprojects, unconventional wind turbines, unconventional gas. Notes. References. Oil sands facts and statistics, Alberta Energy, 2013, retrieved December 28, 2013, Alton, Northeast. Here section Ilmers, C. Wang, J.Y. Suat Bassi, A. Car paragraph K, MV oil shales in the world and Turkey. Reserves, current situation and future prospects, a review. Oil shale. A Scientific Technical Journal 23, 211 Euro 227. ISSN 0208-189X. Retrieved June 16, 2007. Andrews, Anthony. Oil shale, History, Incentives, and Policy. Congressional Research Service. Retrieved June 25, 2007. Bartis, James T. Lautourette, Tom. Dixon, Lloyd. Peterson, D.J. Sachin, Gary. Oil shale development in the United States. Prospects and policy issues. Prepared for the National Energy Technology Laboratory of the U.S. Department of Energy. The RAND Corporation. ISBN 978-0-8330-3848-7. Retrieved June 29, 2007. Breen Dow, K. Global Oil Shale Issues and Perspectives. Synthesis of the Symposium on Oil Shale. 18 November 19, Deline. Oil shale. A Scientific Technical Journal 20, 81 Euro 92. ISSN 0208-189X. Retrieved July 21, 2007. Gordon, Deborah, Understanding Unconventional Oil, Washington, D.C., Carnegie Endowment for International Peace, retrieved December 28, 2013. Dinney, John. A Geology and Resources of Some World Oil Shale Deposits. Scientific Investigations Report 2005 Euro 5294. United States Department of the Interior, United States Geological Survey. Retrieved July 9, 2007. Special Wastes. United States Environmental Protection Agency. United States Federal Government. March 9, 2009. Retrieved December 30, 2009. Francu, Uraj. Harvey, Barbara. Lawinan, Ben. Sert, Andres. Videma, Michael. Format equals PDF. A study on the EU oil shale industry viewed in the light of the Estonian experience. A report by EASAC to the Committee on Industry, Research and Energy of the European Parliament. European Academy Science Advisory Council. Retrieved May 6, 2011. Annual Energy Outlook 2006 inches. Energy Information Administration. February 2006. Retrieved April 18, 2008. World Energy Outlook 2001, Assessing Today's Supplies to Fuel Tomorrow's Growth, IEA, 2001, ISBN 92-64-19658-7, retrieved December 27, 2013. World Energy Outlook 2011, International Energy Agency, ISBN 978-92-64-12413-4, retrieved December 27, 2013. Cole, Michael. Estonian Oil Shale. Oil Shale. A Scientific Technical Journal. ISSN 0208-189X. Retrieved July 21, 2007. Lewis, Jeff, Oil sands crude not as expensive to produce as it used to be. Financial Post, Lewick, Hans. Alternative Technologies for Oil Shale Liquefaction and Upgrading. International Oil Shale Symposium. Tallinn, Estonia, Tallinn University of Technology. Retrieved June 9, 2009. Qian, Jialin. Wang, Jianqiu. Li, Xuan. Oil shale development in China. Oil shale. A Scientific Technical Journal 20, 356 Euro 359. ISSN 0208-189X. Retrieved June 16, 2007. NPR's National Strategic Unconventional Resource Model. United States Department of Energy. April 2006. Retrieved July 9, 2007. Survey of Energy Resources. World Energy Council 2007 pages 93 Euro 115. ISBN 0-946121-26-5. Retrieved November 13, 2007. The Global Range of Crude Oils, ch. Oil Sands Crude, UK, Canada Crude Handout 1, retrieved December 28, 2013. Map of Assessed Continuous Oil Resources in the United States, 2014. Reston, Virginia. U.S. Department of the Interior, U.S. Geological Survey, 2015. External links: Unconventional Resources Center for Energy, World CTL.